Hi, welcome back. So today we'll go into the chapter 5 of S2, which is on sampling. So essentially, when we try to study the statistics of, let's say, some population, let's say you want to do some census on perhaps, for example, how many male versus female in the country. So basically, you don't try to find out exactly how many of Malaysians are male, how many Malaysians are female, and so on. So what you are trying to do here is instead, so let's say this big uh, oval is the population. So this is what we call as the population data. So essentially, what you are trying to do is not to measure all the data from the big population, but instead you try to take some small samples across all your data sets. So of course you want to try to be random so that you sort of like cover the whole population space. So all these smaller data sets that you try to collect, for example, you can try to collect from each of the different states, like for example, Perak, Selangor, Negeri Sembilan, and so on. So you try to collect all these smaller data sets. So all these smaller data sets are what we call as the sample. If your sample is random enough, it will represent what you want to study for the whole population. So essentially, if your sample is random enough, so you will fit a few points. So um, you want to test if the information collected from the sample actually fits the population parameter or not. So this is one thing that you want to test. So technically speaking, this is hypothesis testing. So this is some we sometimes call this hypothesis testing. So what would be the second thing? Sometimes, for example, if your so sometimes, for example, your complete data is limited by some circumstances. Maybe I'm right. For example, it is not accessible for you to look at the whole country, or let's say you want to test how durable some product, you can't possibly test all the products, so you will take random samples and then you uh, try to deduce whether or not all those samples that you take fulfills your population data, which is usually the means and the standard deviation or the variance. So that's why we want to take sample. And if your sample is random enough, if it is a random sampling, meaning that each of the samples that you take uh, has equal chances. So then uh, if it is random sampling, then the sample will represent the whole population. If it is not representative, then it will be biased. So if not representative, then the sample is biased. Okay, so in this particular chapter, you only learn one sampling method, which is called the sample mean. So what is sample mean? Sample mean basically is that you try to take the mean of all the random variables. So sample mean basically means the mean of all the items in the chosen sample. So let's look at one example. And I think it'll be clearer if you look at examples rather than just the definitions. So we will look at dice roll. So if you roll a die, basically this is the probability distribution table. So let's say I roll a die, and this is the probability of getting 1, 2, 3, 4, 5, 6. So each of these probability will be, like, for example, 1/6 across all the boards. So now let's say you want to take the mean of 2 dice roll. So what does it mean? I will try to construct a larger table. So let's say I have 2 dice. I sum them up, the result of it, and I divide by 2 because I have 2 dice roll. So I denote this as, let's say, y. So here I try to find out what is the probability of everything. And beforehand, I know for sure that this should be divided by 36. So I just put it at the side. So what are the possible configurations? So of course, if let's say you roll 1 and 1 for dice 1 and dice 2, you sum them up, you get 2, and then you divide by 2, you get 1. So the smallest number that you can get is 1. So the smallest number that you can get is 1. And then what is the next number? The next number would be if one of it rolls 1, the other one is 2. So 1 plus 2 is 3, and then you divide by 2, so you get 1.5. So you have 1.5, and then you repeat the whole process. You have 2, 2.5, 3, 3.5, sorry. and then 4, 4.5, 5, 5.5, 6. Okay. Let's spread out 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Never mind. I don't have enough space. So let's divide this space properly so that so from 2.5 onwards, I make it larger space. Later on you'll see why. And then 4.5. So 5, 5.5, 6. Cool. So now let's look at the probability by itself. So if you roll 1, what you can get is only both of the dice roll 1. So it means that this is 1 over 36. If it is 1.5, then you have both sides is either 1, 2 or 2, 1. So this is 2. If it is 2, then you can either get 1, 3, 3, 1, 2, 2. So this is 3. If it is 2.5, so it is 1, 4, 4, 1, 1, sorry, not 1, 2, 3, 3, 2. So you have 1, 2, 3, 4. So similarly, you can write down all the different configurations. This should be 5 over 36. This should be 6 over 36. So now let's look at 4. So this will be 2, 6, 6, 2, then 3, 5, 5, 3, and 4, 4. So you will be going decreasing trend. 4, 3, 2, 1. So if you try to sum them up, all these numbers, you'll find that this is 36. So 36 divided by 36, you get 1. So this is a valid probability distribution table. So now I have two probability distribution table. Of course, I can try to calculate the expected value and variance. So for the first one, the expected value for D1, it is given by the sum of xi, pi. So if you try to sum them up accordingly, what you would get is 3.5. If you find the variance of D1, this would be sum of xi square pi minus your mean square. If you do it properly, this will be 35 over 12. So now let's look at the second probability distribution table. So EY will be E D1 plus D2 divided by 2. So if you calculate based on your probability distribution table, you will find that this is exactly 3.5 again. So using the same formula over here. Similarly, you can also find the variance of y, which is the variance of d1 plus d2 divided by 2. So this time you use back the same formula from the table. You will find that this is 35 over 24. So you will notice something. For sample mean, the expected value basically is the same as long as your random variable are coming from the same source. So you cannot sort of like mix, let's say your D1 is dice roll, your D2 is coin toss. You cannot mix it like that. The random variable sort of needs to have the same nature. If that is the case, you will find that for sample mean, the expected value will be the same. The variance will be the variance of the original random variable, which is dice roll in this case, divided by 2. In fact, from chapter 3, so we learned that if you combine two random variables together, this should be ex1 plus x2. So now, this would be ex1 plus ex2. So now let's put this as a dice roll. I mean, we can technically put it here. Yeah, let's write it down. So you have e d1 plus d2 divided by 2. So you can separate this out. D1 over 2 plus e d2 over 2. So we also know that if you have a x, this is a e x. So we can definitely factor this out. And since this is the same nature of random variable, the expected value of d1 is the same as the expected value of d2. So this is half e d1 plus half e d1. So in the end, we get e d1. So this somehow shows that for sample mean, basically no matter how many samples you are taking, the expected value should be the same as the original random variable. Whereas for the variance of x1 plus x2, for example, this is the same as the variance of x1 plus variance of x2. But we also know that the variance of a multiplied with x is the same as a squared, the variance of x. So let's see how we can show it here. So you have the variance of d1 plus d2 over 2. So of course you can separate out like this. Okay. So because of this particular formula, you have 1 over 4, the variance of d1 plus 1 over 4 the variance of D2. So the variance of D2 is again the same as the variance of D1. So that's why you have 1 over 2 the variance of D1. So in general, it doesn't matter like how many sample mean that you are taking. So as long as you are taking, for example, n samples of sample mean, basically your E x bar n. So this is the notation that I use. So x bar means sample mean, and the subscript n means you are taking n samples. So they are the same as the mean of the original random variable. So Ex is mu in this case. If you are taking the variance of x bar n, so this will be sigma square of course you need to divide by n. So the variance of x is sigma square. So this formula stays true no matter how many sample mean you are averaged from. So there is one thing that you need to take note of. So there is this thing called central limit theorem. So what is central limit theorem? Basically, it just tells you that if you have a very large sample size, the distribution of your sample mean is approximately normal. So the mean, so let's say this is your large sample size, it will be approximately normal with the mean from above, and the variance will be sigma squared divided by n. So this is what central limit theorems tells you. So there are two caveats. If let's say, so this I have to put stars. If your x is approximately normal, then your n, a very small n will be enough. For central limit theorem to apply. If your random variable is by itself normal, then your x bar n will be normal regardless of how big or how small is your n. So a general rule of guide of rule, sorry. So general rule is that your n has to be greater than 50 for central limit theorem to be applied. So if you're unsure whether or not that particular random variable is normal or not, then you just look at whether or not n is greater than 50. If it is greater than 50, then usually it is normal. If it is not, then probably you cannot make use of central limit theorem. So that's really what this particular chapter is about. And it is again a very short chapter. So let's look at 3 examples. Sierra needs 5 kg of flour, so she buys 10 bags, each labeled as 500 grams. On average, the bag has 510 gram with variance 120. So what's the probability that she actually buy less? So over here, you already know what is your EX. This is 510. The variance is 120. Okay. So now 5 kg is the sum. So if you want to find the average, you use 5,000 gram divided by 10. So this is 500. So let's write down what is x bar 10 because you buy 10 bags. This is the same 510. The variance of x bar 10 would be 120 divided by 10, which is 12. So you want to find the probability that the mean is less than 500. 500 is what we calculated over here. So you just assume that this x bar 10 is normal with the mean 510, the variance 12. So then over here, this will become 500 minus 510 divided by square root 12. So this will be PZ smaller than minus 2.887, and you just flip it. So let's say this is your bell curve. This is minus 2.887. So this is the area that you want to find. So it means that this is the same as 1 minus PZ smaller than 2.887. So 1 minus 0.998. So what you get is 0.002. So that will be your solution. Question 2. You have the length of an electrical component produced by a company. So you have a probability density function. Calculate the probability that the mean of 40 samples is greater than that value, and then the second part will be the mean of 20 samples is less than that value. So first thing first, you need to calculate what is your mean. So to do that, basically you just integrate from 1.8 to 2.2. X multiply with your probability density function, and then integrate as dx. So this is basically 5 over 2 x squared over 2, and then 2.2 1.8. So you evaluate this, you find that this is equal to 2. Now you find the variance of x. This is the same as, so this time I directly take out 5 over 2, integrate one from 1.8 to 2.2, x squared dx minus 2 squared. So this is 5 over 2 x cubed over 3, 2.21.8 minus 4. So this is 1 over 75. So for part A, 40 samples. So E x bar 40 will be 2. Variance of x bar 40 will be 1 over 3000. So basically 1 over 75 further divided by 40. So you want this to be greater than 2.05. What you will need to do is to perform the calculation as usual. So this is 2.05 minus 2, convert to z score. So this is Pz greater than 2.379. 1 minus Pz smaller than 2.739. So what you will get is 0031. That is part A. So part B is 20 samples, but this time it is smaller than 2.05. So the expected value of 20 will be 2, the same thing, but the variance would be 1 over 75 divided by 20, so it's 1500. So Px bar 20 smaller than 2.05 would be the same as Pz smaller than 2.05 minus 2 divided by 1 over 1005. So this is Pz smaller than 1.936. So refer back to your table, this is 9736. Question 3. The burn time in minutes for a certain brand of candle can be modeled by a normal distribution, mean 90, standard deviation 15.6. So let's say this is your burn time. It is normally distributed by mean 90, standard deviation 15.6 squared. So you have 5 candles, one lit immediately after another burn out, burn total 500 minutes or less. So 500 you divide by 5, it is 100. So this is your mean. Later on we will use that. So now Ex bar 5 would be 90. Variance of x bar 5 will be 15.6 square divided by 5. If you calculate this, this is 14.672. So the probability of x bar 5 smaller than 100, 100 is coming from the one above, would be Pz, convert it to z score, 100 minus 90, divide by the square root of 48.672. So this is Pz smaller than 1.433, and you can just read from the table 924. So that would be your answer. So that's all for this chapter. It's quite short. So tomorrow we will enter the last chapter of S2. Thank you.